Dear student, welcome to NPTEL Phase 2 video course on Geosynthetics Engineering in Theory and Practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course Geosynthetics Engineering in Theory and Practice. This Module 6, lecture number 27, Geosynthetics for Reinforced Soil Retaining Wall. I will now show the recap of the previous lecture. We covered mechanically stabilized segmental reinforced soil wall, geosynthetics reinforced soil wall system, major component of reinforced soil system, precast concrete modular block or panel facing and connection, design of geosynthetics reinforced soil retaining wall partly covered. Now step 4, determine the design factor of safety based on mode of failure. The geosynthetics reinforced soil wall is designed based on limit equilibrium method of analysis. The two limit states are: one, ultimate limit state, actual failure or collapse of the reinforced soil wall, and two, serviceability limit state. That means excessive deformation and or settlement of reinforced soil wall. You have to check the settlement criteria for reinforced soil structure using the conventional method. Now we will discuss about the external stability. In this course we will cover the three parts, and part 1 which we will cover the mechanically stabilized reinforced soil wall, in which we will use this geogrid material, and this have a different strength. So we will see how we can design the geosynthetics reinforced soil wall system using this geogrid material. So this is a kind of geogrid material. You can have the different strength and different types of the geogrid material. So it also has a tensile strength in the machine direction as well as tensile strength in the cross machine direction. Also you have to be taken care about the elongation of the geogrid in the machine and the cross machine direction. So we will use mainly this kind of the geogrid material in part 1. We also use this non-woven geosynthetics material. This is non-woven geotextile material, and we also design the reinforced soil wall using this kind of non-woven geotextile material. And you can see this is the non-woven geotextile, you can wrap it. This we call the non-woven geotextile material. Also we can use that woven geotextile material, and it has also in the machine direction and the cross machine direction, and you can also construct this reinforced soil wall using this woven geotextile material. So we will design also using this material how to design the reinforced soil wall. So this is the part 1 which we will cover with the geogrid and non-woven geotextile material and woven geotextile material. And in the part 3 we will cover this gabion as a phasing element, which we can use the gabion as a phasing element. Also we can have in the form of the strip. Also the gabion as a box as a phasing element. So this we can also cover later on, and we will see the design, how you can design the gabion retaining wall using this kind of the gabion material. This is galvanized mild steel, PVC coated, is hexagonal in shape. So this also we will discuss. And next we will use this waste bottle. This is the plastic bottle. It's kind of the cellular reinforcement. This gives the very good confinement effect. This you can use as a planar form, and we will design this also using this cellular reinforcement, which is made of the waste bottle. You can have also in the different diameter and different height of the material, and how you can design using this waste plastic bottle. Either it is in the matte form, also you can use also in the strip form, like this you can use it. It is also the flexible, it has also the different shape and the size, so you can use also as a reinforcement. So in part 1 we now will discuss with the geogrid reinforced soil wall. So when we will design, then it is required the external stability. You know, external stability, there is a possibility of the geosynthetic reinforced soil wall is sliding. You can see that how the geosynthetic material is sliding. So you have to check up what will be the factor of safety against the sliding. Then you can see this here, the how the wall is overturning. There is a possibility for failure for the overturning. So you have to check what will be the factor of safety against overturning. Similarly, also it may fail due to the bearing capacity. If the soil is very soft, it is required to improve the bearing capacity of the soil or the foundation soil. So also you have to check what will be the factor of safety against bearing capacity. And it is also required, most of the time we do not consider for checking the rotational slip surface failure or deep seated failure or global failure. We can see that failure line is passed beyond the reinforced zone. This also is required to check. So you require to check that what will be the factor of safety against the global stability or rotational slip surface stability or deep seated. So for sliding factor, so you require some factor of safety. It should maintain that what should be the factor of safety against sliding, and it should satisfy this criteria for the design of the reinforced soil wall. So for sliding, factor of safety should be greater than equal to 1.5. For overturning, you require factor of safety greater than equal to 2. Bearing capacity, you require factor of safety greater than equal to 2.5. Overall or deep seated stability or global stability, you require factor of safety greater than equal to 1.3. At the same time, you require the seismic stability. So this factor of safety should be greater than equal to 1.1 or 75% of all static factor of safety. So if you know what will be the factor of safety in the static due to the sliding, overturning, etc., then you have to check up the seismic stability and the factor of safety, at least it should be 75% of the static factor of safety. It is also essential to estimate the settlement, and this settlement you can use the conventional settlement analysis. Now when we talk about the external stability, here you want to check the external wall stability with a uniform surcharge load or ultimate limit state. So, this is the reinforced soil wall with uniform surcharge load. This is the wall, this we call facing element, and this is the height of the wall is capital H. So, you can calculate at any depth what will be the pressure, you can also calculate, and this is the number of the layer of the reinforcement. This is the geogrid here as a reinforcement. I showed you what is the geogrid material. You require what should be the property here in the reinforced soil zone. Here gamma R is the unit weight of reinforced soil, pi R this angle of friction of the reinforced soil zone, and then you require the back of the wall. This is the backfill zone. So, what will be the unit weight of the backfill soil gamma B and friction angle of the backfill soil pi B. You also require the foundation soil, what will be the properties of the foundation soil, and foundation soil this unit weight of foundation soil is gamma of F, and the angle of friction of foundation soil is equal to pi into F. And there also will be the development of the friction between the reinforcement and the soil, which we can express also as a delta of R. Apart from this, there will be surcharge load. Here we are considering the only surcharge, uniform surcharge load, which is designated as W of S with an angle, slope angle also it can be. So, it can change the equation. So, here initially we are considering for external wall stability with uniform surcharge load there, and this is showing the ranking failure surface. We have discussed already how you can obtain the ranking failure surface line, and if this is which is making at an angle of 45 degree plus pi by 2, and this is the toe, and this if the height of the wall is h, and this distance will be equal to 0.7 times the height of the wall, that means 0.78. Now, ranking distribution of lateral pressure. If this is the wall, so we have to check what should be the pressure on the wall, what will be the soil pressure, what will be the surcharge pressure. So, here you can I can show you like this. If this is the wall whose height is equal to h, and this is the facing element, and this is the length of the geogrid reinforcement is the L, and this is the Ws is the surcharge pressure, and this you have to check what will be the weight of the surcharge load. If weight of the surcharge load is equal to W of Q, so W of Q will be equal to Ws into length of the reinforcement is L. That means weight of surcharge load Wq will be equal to Ws into L. And this Wr, this is weight of the reinforced soil. So, weight of the reinforced soil means you know what will be the length, you know what will be the height, and you know what is gamma of R here in the reinforced soil zone, if this is a gamma of R. So, weight of the reinforced soil, that is W of let us say R, will be equal to gamma of R into H into L. So, the weight of the wall will be gamma R H into L. But in case of surcharge load, if the weight of the surcharge load is W of Q, W of Q will be equal to Ws into L. This is Ws, and this is the length of the geogrid material. And we see that there is a soil pressure. So, lateral soil pressure from the backfill, this is the backfill zone. So there will be the lateral soil pressure on the backfill zone, and this soil pressure distribution will be the triangular in pattern, and this PB is the lateral soil pressure from the backfill, and which is acting at a distance of 1/3 of the height of the wall. If height of the wall is h, and then this distance from the base of the wall will be h by 3. So this is the soil pressure which is acting on the backs of the wall. So this is the lateral soil pressure from backfill, which is designated as PB. Apart from this, there is a surcharge pressure. So we check what will be the lateral pressure due to the surcharge load. So due to the surcharge load, you know that there will be uniformly distribution of surcharge pressure, and this surcharge lateral pressure due to the surcharge load is designated as P of Q, and this lateral pressure due to the surcharge load which is acting at a distance of the wall, and this distance is h by 2. So h is the height of the wall. So we know that what are the pressure, what it is acting. So this we have to take into consideration for the design. Apart from this, you see that if the wall moves, then there will be a development of the friction. So this is mu or tan delta. We can say that what will be the coefficient of shearing resistance between the soil and the reinforcement. So that delta is called angle of shearing resistance between soil and the reinforcement. If there is a possibility for any cohesive soil, then CA also you have to take into account. So this CA, what we call here as a adhesion between soil and the reinforcement. So if it is the entirely cohesionless soil, then you can take only consideration for the mu or the tan delta, what we call the coefficient of shearing resistance between soil and the reinforcement. But if there is a both cohesive and the cohesionless soil, then you have to consider both these factors, mu and also the adhesion. When it is interact with the other material, we say that it is a adhesion. So CA adhesion between the soil and reinforcement. So you have to consider both these factors. One is the friction factor, another is the adhesion factor. So this you have to be considered into the design. Now if the wall slide, so you have to calculate that what will be the factor of the safety against the sliding. So wall may move in this direction. So you have to calculate what will be the factor of safety against the sliding. So factor of safety against the sliding is equal to summation of horizontal shearing resisting force divided by summation of horizontal driving force. So what are the resisting force and what are the driving force? So total force is that PB and the PQ. So what is PB? PB is equal to half into KAB into gamma B into H square. Is gamma B here, the backfill soil unit weight of the soil. So PB will be equal to gamma B half KAB gamma B into H square. So you can write that PB is equal to half into KAB into gamma B into H square. Similarly PQ due to the surcharge. So PQ also you can write is equal to KAB into W of S into H. So, where KAB is equal to tan square 45 degree minus pi b by 2 or coefficient of active pressure of backfill soil behind reinforced zone. So, we know that what should be the pi b value. So, you can calculate what will be the KAB value. If you know the KAB value, so you can calculate that what should be the height is known to you, gamma b is also known to you. So, you can calculate PB. Similarly, you know what will be the surcharge load, you know the height of the wall, you know KAB. So, you can calculate the P of Q. So, all the parameters can be calculated. Now, this is the force and there will be also the resisting force. This is the resisting force. So, resisting force will be mu into weight due to the reinforced soil wall and weight due to the surcharge. That means mu into WR plus WQ plus due to the adhesion the CA into L, CA into L. So, these are the total resisting force. So, resisting force can be written mu into WR mean gamma R HL plus surcharge load WQ is equal to WS into L plus CA into L. So, you can see here this total resisting force. So, we can write mu into WR plus WQ plus CA into L is equal to mu WR means gamma R H into L plus WQ is WS into L plus CA into L. Now, if you substitute this form, this equation, that factor of safety again is sliding, horizontal resisting force by horizontal driving force. So, driving force you know this plus this and the resisting force you know this. So, if you substitute you can have this equation, factor of safety again is sliding, that is mu into gamma H L plus WS into L plus CA into L divided by KAB into H 0.5 gamma B into H plus WS, and this factor of safety again is sliding should be greater than equal to 1.5, and if there is no adhesion, so then CA will be the 0. So, only you take into consideration this part. So now you will be able to calculate that what will be the factor of safety against this sliding. Now, we will discuss factor of safety against overturning. So, factor of safety against overturning means is equal to summation of the resisting moment divided by summation of overturning moment. Now, what is overturning moment? About the toe. So, you have to take the moment at the toe. For example, this you know, this is the toe and this is the toe, and you wanted to take the overturning moment, not sliding, there is a overturning moment. So, overturning moment about the toe, which we can designate it at M of O of V. So, this M of O V will be equal to, you take a moment at the toe, that means PB into H by 3, the distance is H, PB is the force due to soil, so PB into H by 3, and due to surcharge this is PQ and this distance is equal to H by 2, that PQ into H by 2. So, overturning moment MOV will be equal to, that means this will be equal to PB into H by 3. So, you can write that PB into H by 3 plus due to the surcharge you take the moment at the point toe, that means this is PQ into H by 2. So, again you know this value of what is PB and what is PQ. You can see here that PB we have calculated earlier, KAB into gamma B into HQ by 6, because we know that what is PB here, and also you know what is PQ here. So if you substitute this value, then you can obtain that PV into H by 3 will be this part, and then PQ will be the KAB into WS into H squared by 2. We have calculated what is PQ. So you know that what will be the overturning moment about the toe, and also you require resisting moment about the toe. So resisting moment, let us say here that weight of the wall, and this is due to the weight of the surcharge. So here is the weight, you take a moment here, this is the resisting. So this is passing through the middle of this wall. So if this is WR and this will be L by 2. So resisting moment, if you take the moment at the toe, so WR into L by 2 plus due to the surcharge, this is WQ into L by 2. Now we know that what is WR, you know gamma R H into L, you know what is WQ, WS into L. So if you substitute this value here, you can see that MR is equal to gamma R H into L plus WS into L by 2. So if you calculate, you can have MR is equal to gamma R H into L squared by 2 plus WS L squared by 2. Now you find out what will be the factor of safety against overturning. You know the equation, factor of safety overturning is summation of resisting moment by overturning moment. That means MR divided by MOV. So you substitute all this value and you can obtain the factor of safety against overturning, that is 3 into WS plus gamma of R into H, this divided by KAB into gamma B into H plus 3 WS into H by L whole square, and this factor of safety value against overturning should be greater than equal to 2. So it should satisfy this criteria against this overturning. Now factor of safety against that bearing capacity if the foundation soil is poor, and how you can calculate the bearing capacity of the soil. So what we use this part, the foundation soil. So we take that measure of stress distribution for ground bearing pressure, and we have to calculate that what should be the eccentricity, that means E. E is important here. Now eccentricity E can be written as what will be the length at the bottom, this divided by 2 minus of x bar, and I am showing here that L bottom divided by 2 minus x bar is equal to MOV by V, and this x bar is equal to MR minus MOV divided by V. V is the total vertical load. So you know that what will be the total vertical load. So that total vertical load will be equal to WQ plus W of R. So whatever the vertical load, V will be equal to WQ plus W of R, and you are to calculate what should be the eccentricity, and this eccentricity value is should be less than equal to L by 6, and no tension will develop beneath the footing. So from the measure of distribution, the acting length, if we consider L dash will be equal to L minus 2E. So you have to consider always that acting length, that means L minus 2E zone only, and this measure of pressure distribution for ground bearing capacity is recommended. Now there is a possibility for two types of the bearing capacity failure. One is the general shear. For the maximum vertical stress, so sigma V maximum is equal to sigma V maximum divided by WQ plus WR divided by L minus 2E. So it acts in that acting zone only, L minus 2E. So sigma V maximum is equal to, you know that what is W of Q, you know Ws, you substitute, and then you can have gamma R into H plus Ws divided by 1 minus 2E by L. And eccentricity MO V by V, so you know this PV into H by 3, this is PQ into H by 2 divided by V means WR plus WQ, and from here you can calculate that what is the E value. E value will be KV into H square into gamma V into H plus 3 into Ws divided by 6L into gamma of R into H plus Ws, and it should be less than equal to L by 6. It should be. And then you can calculate what will be the sigma of V maximum. So you substitute this E value in this equation here, and then you can calculate the sigma V maximum, which sigma V maximum is equal to gamma R into H plus Ws divided by 1 minus KV gamma V into H plus 3 Ws divided by 3 into gamma R into H plus Ws into H by L whole square. So you know what will be the sigma V maximum. Now you have to calculate that ultimate bearing capacity of the soil, or Q of ultimate, and this is known to you. So ultimate bearing capacity Q ultimate is equal to Cf into Nc plus 0.5 gamma F into L dash into N gamma, where L dash is equal to L minus 2E. E is eccentricity. So you know eccentricity, you know what will be the length of the reinforcement, so you can calculate what will be the L dash. And here Nc and N gamma are the dimensionless bearing capacity factor. So then you check what will be the factor of safety against bearing capacity is equal to Q ultimate divided by sigma V maximum, and it should be greater than equal to 2.5. If it satisfies, then it's okay. Now for the locals here, if the subsoil is poor, so bearing capacity is to be increased. So what you can provide with the 3 layer of the geogrid, or the geocell matrices can be provided beneath the foundation for ground improvement. So there will be the different types of the ground improvement. You can go ahead with the prefabricated vertical drain, you can go ahead with the encased stone column, which will show you later how to design the encased stone column, and also you can go for the number of the layer of the reinforcement to improve the bearing capacity of the foundation soil, or you can go for the geocell, which will give the confinement effect, very good confinement effect. So geocell or matrices of the foundation. There are different system for the ground modification or the improvement, so you can adopt and you check the local shear. Now next is the slip failure or overall or deep seated stability or global stability. For deep seated or overall stability, use the rotational slip method by classical slope stability analysis. Failure surface will pass completely outside the reinforced soil mass. Computer program is available to solve the problem. So you check that what will be the factor of safety against the overall stability, and that factor of safety against overall stability should be greater than equal to 1.3. Particularly in case of an unstable hillside, the potential compound failure may occur. The overall or global stability should not be avoided. Now external stability for seismic loading. The conservative pseudostatic Mononobe-Kowabe analysis is recommended by ASTO and FHWA guideline for the seismic design of geosynthetics mechanically stabilized earth wall. Apart from the static thrust, a seismic thrust or the dynamic horizontal thrust, which is designated as PAE, is also acting on the reinforced soil wall during an earthquake. So most of the time we don't consider the seismic effect on the reinforced soil wall, but it is very important to consider the seismic effect on the wall, because you know it is lot of earthquake related problem on the infrastructure. So, you should consider the seismic effect. So, this is the reinforced soil wall. As usual, there is a surcharge load. This is the length, this is the height of the wall. So, this is the dynamic horizontal thrust which is acting on the reinforced soil wall during an earthquake. Here, this distribution is slightly different. So, it is inverse. You can see it is increasing like this, and this is the dynamic horizontal thrust PAE, which is acting at a distance of 0.66 or 2/3 of the height of the wall. So, this thrust we will consider 2/3 of the height of the wall. So, this you should remember in case of the dynamic horizontal thrust when it is acting on the reinforced soil wall, and what the dynamic thrust is acting and what will be the distance from the base of the wall. So, this is 2/3 of the height of the wall. Now, we have to calculate that dynamic force. So, dynamic force we have to use the PAE is equal to 0.375 alpha m gamma b into h square, which is given Seed and Whitman 1970, and then the alpha m is equal to 1.45 minus alpha 0 into alpha 0. This is Sregrestein and Bastig 1988, where alpha m is the maximum wall acceleration coefficient at the centroid of the wall mass, and gamma b is the unit weight of the backfill, and h is equal to height of the reinforced soil wall, and alpha m is equal to 1.45 minus alpha 0 into alpha 0, where alpha 0 is the maximum ground acceleration coefficient. For an example, in a zone 3 as per IS code 1893/1984, suppose for a particular zone, if that alpha 0 value is 0.04, so you can calculate what is alpha of m. Alpha m is equal to 1.45 minus alpha 0 into alpha 0. If you know the alpha m value, you can substitute this alpha m value in this equation, and gamma b and h is known. So, you can easily calculate what will be the dynamic force which is act at a distance of 2/3 or 0.6 times the height of the wall from the base of the wall. So, that you can calculate. Now, the horizontal inertia force, that is PIR, this defined as PIR is equal to m into alpha m, where m is the mass of active zone of reinforced wall with base width of 0.58, or PIR is equal to alpha of m gamma r h into L. This is Seed and Mitchell 1981. So, this is gamma r is unit weight of the reinforced zone, L is equal to length of the reinforcement, h is equal to height of the reinforced soil wall. So, here one to interesting to note that 50% of seismic thrust, that is PIR, is to be considered. So, reduction in PI is due to the fact that two forces are unlikely to peak simultaneously. So, here you should remember that 50% of seismic thrust of PIR is to be considered into the design. So, you add all the forces to determine the total horizontal active force due to the seismic loading. That means that what is the horizontal component of the active earth pressure due to the retained backfill soil, what will be the horizontal active earth pressure due to the surcharge, and seismic surcharge, that is PAE. And as I mentioned that 50% of the horizontal inertia force PI are also taken into consideration. So, all the forces you have to take into consideration. Now, you have to check due to the seismic effect. You have to check for the sliding due to seismic loading. First you calculate the what will be the resisting force, same of the static condition. Then calculate the total active horizontal force including the total horizontal force due to the seismic loading. Check dynamic factor of safety will be equal to 0.75 into static factor of safety, and you can see this equation, the factor of safety, the sliding due to seismic is equal to the resisting force divided by total active horizontal force, and this should be greater than 1.5 into 0.75. If in the static case this factor of safety is equal to 1.5, in case of the dynamic that factor of safety will be 1.5 into 0.75. So it should satisfy this criteria, what will be the factor of safety due to the sliding and for the seismic loading. Similarly, B, you have to check overturning due to seismic loading. So you calculate the resisting moment, same for the static condition. Calculate the total driving moment. Then horizontal forces PIR is acting at the center of the gravity of the reinforced zone. Then dynamic horizontal thrust PAE is acting at a distance of 0.6 times the height of the wall from the base of the reinforced soil. So you check what will be the factor of safety against overturning due to the seismic will be equal to total resisting moment divided by total driving moment, and that should be greater than 0.75 into the factor of safety due to overturning in static is 2. So it should check that it should satisfy the criteria factor of safety against the overturning due to seismic effect. Step 5, check internal stability of the geosynthetics reinforced soil wall. Ultimate limit state. So allowable tensile strength of geosynthetics and the geosynthetic soil friction parameter play a very important role. The wide width test of geosynthetics should be conducted according to the ASTM or other test standard to determine the ultimate tensile strength of geosynthetics. So you know the ultimate tensile strength, then you have to calculate what will be the allowable tensile strength. That means that will be equal to ultimate tensile strength divided by cumulative reduction factor. You know that cumulative reduction factor, that is the reduction factor for the creep, reduction factor for the installation damage, reduction factor for the biological degradation, reduction factor for chemical degradation, etc. So all those factors you have to take into consideration, and then you are to calculate what will be the allowable tensile strength of the geogrid material. Now you require the long term design strength, that is LTDS. So that is T required should be less than equal to T of allowable. It should satisfy. Now we will discuss the internal stability. For internal stability, you require spacing of the geosynthetic reinforcement. What should be the anchorage length of the geosynthetic reinforcement? What should be the connecting state between the geosynthetics reinforcement and the wall panel? These are very important. Most of the time we don't consider the connecting strength because structure may fail if you don't consider the connecting strength between the reinforcement and the wall panel or the block. So there is a possibility for the failure due to the slippage, failure due to the connection. So you have to be proper design for the internal stability. So you need the spacing. If this is the wall, you need what will be the spacing between the two reinforcements. This you have to design for internal stability of a geosynthetic reinforced soil wall. You should also require what will be the length of the reinforcement. So you have to calculate what will be the anchorage length. If you know the anchorage length of the reinforcement, then you know that what will be the total length, then you can deduct or you can determine this, then you can determine the total length of the reinforcement. Knowing this, this angle is 45 plus pi by 2, so internal angle 45 degree minus pi by 2, so this portion also you can calculate. At any depth you can calculate. So if you know this and if you know anchor length from the pull out, and then you can calculate what will be the total length of the reinforcement. So you require what will be the total length, you require what will be the spacing, and at the same time you require that what should be the connecting strength. This you can see how the geogrid is connected with the panel or the block. So this is a segmented block, so geogrid is connected with this, so there is a possibility for the failure. So these all you have to check. So determine the maximum developed tensile strength T required and vertical spacing. Here this is a basic concept of evaluating the required tensile strength, and this is the reinforcement here, also it is here. You can take this is also reinforcement here if you take in between. So from here to here, so this is the S of B spacing between the reinforcement, and this is the fascia, and this is the reinforcement, and this is the maximum tensile force, the T maximum is acting, and this you know the failure plane, okay, and this is active zone and this is the passive zone, where there is a vertical force is sigma of V is acting. So sigma H will be equal to K into sigma of V, and sigma V you know at any depth, you know the unit weight of the soil in the reinforced zone. So sigma V will be equal to gamma R into Z. So sigma H will be equal to K into gamma R into Z. So this is the basic concept for evaluating the required tensile strength of the geogrid material. The maximum tensile force without considering any shear between the slices and the facing can be expressed as T required is equal to K into sigma V into HV. You know K into sigma V is equal to sigma H, and HV is the spacing between the two reinforcement. For geogrid, T required is equal to HV into sigma H by C of R. This is important, C of R, where CR is called coverage ratio, that is width of the reinforcement W, center to center horizontal spacing between the two reinforcement, that is S of H. So I will just show you that what is that coverage ratio. So you can see here, this is the geogrid strip, this is the geogrid strip, and this is the W is the width of the geogrid. This is the width of the geogrid. This is also width of the geogrid. And this is the SH. That means SH is the center to center for horizontal spacing of geogrid. So you are placing a geogrid strip like this. So coverage ratio, this is important. The coverage ratio, which is designated as CR, is equal to width of the geogrid is W divided by this center to center horizontal spacing SH. So coverage ratio CR is equal to W divided by SH. So when you say that CR is equal to 1, that means reinforcement is continuous and cover 100% in the plan view. So you are entirely placing the reinforcement. So it is continuous, cover is 100% in plan view. Whereas if the CR value is equal to 0.6, that means reinforcement are covering partly, that means 60% in plan view. So in case of 60% plan view, you can provide the reinforcement in the form of geogrid strip. So, you can reduce the quantity of the geogrid when you are using this coverage ratio. So, you can save the amount of the geogrid material. So, this coverage ratio, because this is very important when we will put some example. So, when we will design this, so we will consider this coverage ratio CR. So, you can design that when CR value is equal to 1, we can design for CR value is equal to 0.6. One can go for the defined CR value maybe 0.5, 0.4 etc., 0.7, but you have to see that which can give the proper stability of the reinforced soil wall under what coverage ratio. So, that also I will show you with some example. Now, sigma H is equal to sigma Hs plus sigma of Q. What sigma H is equal to soil pressure, that is gamma H into Kr. Sigma H Q is equal to surcharge pressure, that is Kr into Q. So, total horizontal earth pressure sigma H is equal to gamma H into Kr plus Kr into Q, where Kr is equal to tan square 45 degree minus pi r by 2, where pi r is equal to coefficient of friction in the reinforced soil zone, Kr is equal to coefficient of active earth pressure in the reinforced soil zone, and H is equal to height of the wall. So, generally the vertical spacing of the reinforcement is between 0.2 meter to 0.8 meter for mechanically stabilized earth wall or reinforced soil wall. You can go 1 meter also, but it is always preferable that you can go for the 0.8 meter for stability point of view. For geosynthetics wrap face wall, the vertical spacing between 0.2 meter to 0.5 meter, and for modular block wall face, vertical spacing is twice the width of the modular block or 0.8 meter, whichever is less. This is as per ASTOB standard specification for the bridge in 1996 with 1997 interim. If required to determine the embedment length LE of the geosynthetics reinforcement. So, here you can see this is the reinforcement, length of the reinforcement is L, and this is the L of E, or which we call anchorage length. So, from the pull out you can calculate that what will be the anchorage length LE. So, you know that SB into sigma H into Fs pull mean factor of safety against pull out failure will be equal to 2 into L into E, LE Ci sigma V tan pi r dash into Cr. Here Cr is the coverage ratio and Ci is interaction coefficient determined from the pull out test. So, you can calculate this interaction coefficient from the pull out test. Suppose if CR value it may be 1, and then from the pull out test you can calculate the what is Ci value. You can conduct the direct shear test of the soil and determine what will be the pi or C value. Then you can perform the pull out test from where you can calculate that what should be the anchorage length. So, if you know this anchorage length, that means from this equation LE is equal to SB into sigma H into Fs pull out divided by 2 sigma V Cr Ci into tan pi dash. So, from the pull out test you can calculate Ci, and Cr is the coverage ratio that depends upon whether you are using that 100% planar or 0.6 or 0.5 etc. So, if you know, then you can calculate the what will be the anchorage length, which is important to us. You know the how to calculate the spacing SB, you know how to calculate the sigma of H, and then you consider what will be the factor of safety for pull out. So you can calculate LE. So if you can calculate the LE, then you can calculate LR, because if this angle is 45 degree plus pi by 2, so this angle will be 45 degree minus pi by 2. So this length at any distance, so you can calculate LR. So if you calculate LR, then you can calculate the total length L is equal to LE plus L of R. So you have some idea about the design of geogrid reinforced soil wall, how you have to determine the external stability, internal stability, and also how you can calculate what will be the sliding resistance, what should be the factor of safety against the sliding, factor of safety against the overturning, also factor of safety against the bearing capacity, and factor of safety against the deep seated failure or the global stability. Also for the reinforced soil retaining wall is have learned that what will be the spacing between the two of the reinforcement, what should be the length of the reinforcement, what is the anchorage length. So you will be partly able to design the geosynthetic reinforced soil retaining wall. With this I ended up the lecture today. Thank you for listening.